Okay, so let's continue with the isolated footing problem, having 100 mm thick and 500 mm width. Okay, so its properties is now concrete. Okay, with a Poisson ratio of about 0.17 and an elasticity of 21.7 gigapascal. Okay, let me check that. Poisson ratio 0.17, elasticity 21.7 gigapascal, and thickness 100 mm. Okay, so with the supports here, again, it's a plate mat with a 50,000 kilonewton per cubic meter modulus of subgrade. And since our mesh is, this is 0.125 by 0.125, multiply that with our subgrade, you will obtain a K, or because this is our tributary, okay, then you will have a K per node of, and of course, we will also consider the 1/4 of the total tributary. You will get 195,312, okay, Newton per meter. Okay, so that's the total K contribution of each node, no? Per plate. Okay, so that's from 50,000 times 0.125 by 0.125, and then get the 1/4 of that, and you will obtain that. Okay, so goes this. The loading is 2 kilonewton, the center, and that's it. Let's now analyze that. And if you check on the post-processing, the maximum and according to our STAAD run, the maximum deflection is 0.16 mm. Okay, so basically, with that maximum deflection, you can already double check if with the corresponding subgrade modulus of 50,000 kilonewton per cubic meter, uh, did you satisfy the allowable deflection or settlement of the soil? Okay. Anyway, so this 0.16 is almost negligible, right? So anyway, for the sake of computing the using a finite element approach, okay, so 0.16, so let's go back to our SMATH. So let's check first our stiffness matrix. Okay, so we have 21.7 gigapascal, Poisson ratio of 0.17, and the thickness of 0.1, and the size of the mesh of 0.125. Okay, so which is consistent with our mesh here. Now, okay. Now the additional information that we have to input here is this K that we were able to compute here. Okay, so that's the contribution per node of the soil subgrade modulus. Okay, and again, I already explained this addresses of the from the original stiffness matrix. Okay, because they corresponds to the vertical displacement or stiffness of our plate. Okay, so we're going to add this to each vertical stiffness. Okay, so let's calculate. Okay, so we're done with the calculation. So this is our stiffness matrix per plate, no? Uh, Incorporating the stiffness from the soil subgrade modulus. Okay, and then erase this. So we will copy paste that. Copy this, and then let's proceed to our next SMATH code, wherein we will paste here and the updated stiffness matrix, and we will loop again to 16 because we model the foundation by 16 elements. Okay, so after pasting there, okay, let's now define other parameters. Okay, so we have 25 nodes and we have 16 plates. Okay, my reduced variable now is 75 because unlike with the previous problem, the isolated foundation is going to be displaced in all directions, right? So it's not only the vertical displacement, but each node will also rotate, right? So therefore, since we have 25 nodes, right, here, so since we have 25 nodes, each node, all nodes here are going to be displaced by a certain amount of vertical displacement and a certain amount of rotation on both direction. Okay, so therefore, since we have 25 nodes, 25 times 3 displacement per node, that will be about 75 DOF, 75 displacement. Okay, now, so that's why this is now 75. As compared to our previous problem wherein we have a cantilever or fixed edge plate. Okay, so our reduced variable there is the interior nodes. No? So it's a different case with our foundation. Now, what is this LOC? This one is for the computation of the base pressure. Okay, so I will choose, for example, now to determine the base pressure here at node 13. Okay, remember, in design purpose, once you get the base pressure at a certain location, you will compare that with the allowable soil bearing capacity. All right, so that's the purpose of obtaining the base pressure. So the base pressure okay, so 13, node 13 corresponds to DOF 37, no? Because 13 times 3 is 39. So the vertical displacement corresponds to 37. Okay? So base pressure should be less than the allowable SPC. So that's the general rule, okay? When in terms of design. Next, this one, the mod sub variable is of course the value here that we computed, the 195,312, the stiffness per node contribution. So this is again required in computing the base pressure. Okay, next. So the rest are all the same with our previous problem. Okay, so this one is an updated BU and BB matrix from here. So unlike with the previous problem, in isolated foundation, remember, as I said earlier, all nodes, all degrees of freedom will be solved, no? All of them shall be solved, no? All of them should be determined. Okay, so that's why it's up to it's from 1 to 75. Okay, so therefore our S matrix will be 75 by 75. So from the formula T equals SD, okay, our S will be 75 by 75. Okay, therefore our D displacement is 75 by 1. And of course, our force vector is also 75 by 1. Okay, and of course, its address is up to 99. Okay, so that's why it is AI 25 to AI 99. Okay, next. Okay, so same formula as before. Okay, now remember the load is 2 kilonewton at the centroid or at the center, so which corresponds to 37. Okay, again, the load is here, acting here, 13 times 3, 39, minus 2, that is DOF 37, which means a vertical load, assuming you have a reaction from the superstructure, okay, and you have an isolated footing to be designed. Okay, then what else? Okay, so let's try to change the value of the force, so that we can see the consistency of STAAD. So let's make it 4 kilonewton. So we'll also change this here. Make it 4. Then modify, yes, close. Save. Then run analysis. Okay, of course, let's find out the displacement first. So the maximum displacement is 0.325 mm. Still almost negligible, right? Because that means we have assumed a very stiff modulus of subgrade reaction, grade of 0.325. So update this force and then calculate. Okay, so we are getting 1, 2, 3.29 mm, okay, as compared to 0.325 with STAAD. Okay. Okay. Anyway, let's double check again the result. So assuming the displacements and is quite the same, almost the same. So let's find out the plate results. Plate results, say MX. Okay. So let's say I would like to verify the plate moment of plate number 7. Okay. So in our spreadsheet here, so we'll just update this. So let's check if it's plate number 7. So I'll move here, corresponding to plate number 7, and Control Shift Enter, update. Then by the way, no, let's verify this also. 0.17, a thickness of 0.1, elasticity of 21.7 gigapascal, and mesh size of 0.125. Okay. Okay, so this should be the displacement, and this is the corresponding moment. So let's see. Calculate, recalculate. Okay, so 0.37, almost the same. So we should get about 0.37 kilonewton meter per meter. Okay, and as you see, we almost, yeah, it's almost the same. Right? Almost the same moment value. Okay, that's one. So we got almost the same 0.37 on both MX and MY. Okay, so the displacements is almost the same. The moment values also the same. How about the base pressure? Okay, so let's check base pressure. Apply. Okay, so according to this result, the base pressure at node 13 is about 16 kilopascal. Okay, 16 kilopascal. And let's check what did our code obtain. Yeah, so we are able to get 14.45. Okay, by the way, the formula of our base pressure is, remember, this is from our modulus of subgrade reaction that we assume or that we input. This is basically from a conversion from mm to meters, and this one, remember, is the displacement. We are getting the displacement of node 37 because our LOC, remember, is node 13, which corresponds to DOF 37. Okay, so 16 kilopascal. Okay, and our area is, oh sorry, our mesh size is 0.125. 0.125. Okay. So basically, if you know your spring value here, which is this one, then you also know the corresponding displacement at that node, which this one provides. Okay. Which is basically what? That's about 0. I forgot. It's about 0.3 earlier. 0.32 mm. Okay, multiplied by the modulus of subgrade of 195,312. Okay, divided by the mesh size. Okay, which is 0.125. Okay, and that's your base pressure. So almost 16 to 14. According to this diagram, the base pressure is uniform, right? So let's verify. No? Let's say we wanted to check base pressure at node 7. Node 7. Okay, so we will update this. So node 7. Yeah, so let's update this. So if it's node 7, what's the LOC value? 7 times 3, 21. So that will be 19. Okay, so that will be 19. Okay, next. Let's also update the okay, we're done with the base pressure. How about the plate moment? Let's try plate number 5. Okay, plate number 5. So I'll update plate number 5. Update this. So I'll move here, then Control Shift Enter and save. Okay, so that basically updates the moment of, and then also you like to update the displacement here. Say what's the displacement at node 7 also? Node 7. So that is 19, no? 19. Okay. So that's it. So let's calculate. Okay. So at DOF 19, our displacement is 0.27. 27. Anyway, let's verify that later. How about the moment at at plate numbers 5, right? Plate number 5. Check that. Yeah, according to STAAD, we got 0.05 and 0.25. So as you see, it's almost the same. 0.05, 0.05, 0.25, or 0.28. Okay. IMXY is 0.03, almost the same. Okay. So how about the base pressure? Base pressure, according to STAAD outputs, is also all uniform 16 kilopascal. Let's verify that here. Yeah, so we're getting almost the same. 14 earlier, 13 to 16 kilopascal. Okay. Of course, it's more on the rounding off of STAAD. As you see, there's really a variation, no, of the base pressure. Okay, how about the displacement? Here it's 0.321, okay, according to STAAD, while we got point 20 something, right? 0.27. Okay, so those are discrepancy, which resulted to a discrepancy also in the base pressure. Okay, but those are is is almost negligible in terms of its value. Okay, so that's it. So you now know how to use the plate stiffness matrix application also to an isolated footing modeled as finite element. Okay.